Hello everyone, today we are going to talk about asymptotic analysis and big O notation. As you may know, big O notation and asymptotic analysis are very important topics in algorithms as well as in mathematics. So the reason why we want to use this analysis techniques is to identify if functions are growing or like shrinking, and if you want to compare with them with one another, so we will be able to compare those algorithms or functions, and as a result we would be able to set some boundaries, so we would know if this function is growing, it's not going to pass this line, and then in this way we can compare the algorithms we can use or other functions that you would like to analyze. So let me start with like quick examples to express like what I mean by this. So here, I would like to talk about three different functions. These functions, as you all see, they are, sorry about that. These functions, as you all see, they're all growing. Like this one, and this one with n cube, and like plus some log n here as well. So what is common with these functions? When I first look at to the functions, and I see that like the common thing about these functions are the n cube term. So the n cube term actually dominates the functions. So can I say, so this function is growing by n cube and like it can be upper bounded by n cube? In the first place, yes. But if you look at this first function here, you'll see this coefficient here, 1 over 100. So what if n is actually 5, and would it be like a dominating term in this equation for n cube? No, it won't be. So this means that we need actually some values to validate that our assumption is correct. Yes, it seems that n cube is like dominating, but we need some other coefficients like the constant here, for example, with which constant and for which n value, we call it n0 value, it's going to be greater than that. And then you can prove that it's actually, this function is bounded by n cube. For this reason, in big O notation, we need the C and N0 pair. So here in this figure, if you look at this is the N0. So for large enough n, we talk about, for the asymptotic analysis, we are not going to focus on the smaller part here, instead, because like the functions can grow in time. And if you look at for larger n, which is like greater than N0, for larger n here, so this function here, fn function, can be bounded by another function, which is g of n, c times g of n actually. And when I write something like this, and if I'm eligible to upper bound something, it means that f of n is equal to big O of g of n. Likewise, for the lower bound, I can say the same thing for the omega sign. So what we understood from this topic, what we need is like some c and n0 pair, and we can say c n cube with some c and like some n0 can be upper bounded by n cube. This function can be upper bounded by n cube. So let's discuss more about the big O notation. So if f of n is less than c n cube for some c and n0, so we can say c n cube is an upper bound. And that upper bound means actually the big O notation itself. So big O notation here, it means that it's not like we are not looking at the worst case scenario. We are just looking at a function that can be upper bounded by some other function. Why we need that? Because I want to be able to see like in the future of this like growth, what's happening to the function. Like, can I talk about, okay, this function is like taking this time, but can I say it can be upper bounded, the limit of this would be this function. So the growth will stop somewhere, or I know that the growth will continue under these conditions. So I'm not talking about any kind of worst case scenario. these are all about bounds. For the lower bound, for omega notation, as you see, for some d and n0, of course, fn needs to be greater than d times n cube for the other example we mentioned. So in this case, f of n is going to be omega of n squared. So here, as you see, the f of n, let's say something like linear function here, if I draw it this way. So the d times g of n will be the lower bound, c times g of n will be the upper bound. So this means for upper bound, I can go like wherever I want to go actually. Like if I want to do n to the 4, n to the 5, I can do that. Like if n squared is something like this, if n cubed is something like this, if n to the 4th is something like that, these are all upper bounds because still f of n would be under that line. So what is the point here? Like what do I care about here? What I care about here is actually the closer to the function itself, like here, if I can lower this upper bound and increase this lower bound a little bit, so I will get more precise information about this f of n, like the bound information. Otherwise, you can just upper bound with any other functions. So here's an example. So 5n squared is big O of n cubed, and so this doesn't have any like the ratio or something else. So we can select any c of c and n0, and then we can say 5n squared is actually big O of n squared for some c and n0 pair. But at the same time, if I say n cubed for this, and if I gave like a trivial numbers for trivial pair numbers for this c and n0, so it would be n cubed as well. So yes, it will be big O of n cubed, but at the same time, it's a loose bound. Like it's just very high, and like I don't like to prefer that way. So if it is like n squared, I would prefer that. And if you can find me a pair for like 0 and n0, that's perfectly fine. What about this? N cubed is equal to big O of 5n squared. So first of all, like 5 here, the constant should be 5. Like you can't write like 5 big O of like 5n squared. It's basically big O of n squared. So the meaning of this equation is, can you upper bound n cubed with an n squared? So if n cubed is something like this, and the n squared is going to be somewhere here, right? So you cannot actually upper bound n squared with like to the n cube, because n squared is definitely, for large enough n, it will be smaller than n cube. But you can actually lower bound it. That's something you can do, because with some d value and n0 value. So here I wanted to discuss that like big O notation is actually an upper bound, and the omega notation is a lower bound. So, and these lower bounds are flexible. There is no like certain lower bound for the equation. So what we want to do is, as possible, like we try to make it more to the case specific. So not a loose bound. Instead, we want to create some tight bound. So for another example here, I would like to talk about the sorting example. Why am I choosing this? Because like we confuse this. We try to get the idea of like the worst case scenario here, and then end up mixing the upper bounds and the worst case scenarios. So here, insertion sort. For the insertion sort, you have some array here, and then you start with this element, and then you go next, and then compare these two elements. If, like in this case, 3 is smaller than 4, then you replace 3 with 4, right? So you basically go n times for this. And if you're comparing all of the elements, you're comparing n times like this. And then you do this basically, if it is not sorted at all, in n squared times, right? Because you will go n times to the end, and you will be doing n times to the n comparisons. So which makes n squared. So can I say this is the worst case for insertion sort? Yes, because what else can I do? Like, I'm going basically starting from 1 to n. I'm going through each element, and I'm comparing each element with each other. So I'm basically doing the ultimate work here. So what could be the best case scenario for this? If the array was all given sorted or like same, whatever, let's say it was sorted actually like this here. Let's take the results. So you go and compare 1 and 2. You don't change anything. Here you come to the 3. You don't change anything. In the end, what you would do is n operations. So the best case scenario is n operations. And the worst case scenario is n square operations. So to make a note, like any number occupies O1 time and also can be read in O1 time. That's our assumption is. And you can basically do any kind of calculations with those O1s. But here, I have n elements, large enough n. So the worst case is n squared, and the best case is n. So how would I represent these cases with big O notation, or like bounds, like with omega notation? So if I'm saying like this has like several outcomes, this is n squared. Let's say this is n squared. Let me see if I'm actually, okay. N squared, and this is n. So if I want to upper bound this, I can upper bound this with the best case of the upper bounding with n squared. Why? Because in the worst case of this algorithm, it takes n squared times. So if I say for an upper bound n, it wouldn't work because like it might take n squared times. So it can be n cubed. It can be n to the fourth. It can be n squared, but then we need to prove that for some certain c and n0 values, it's n squared. And anything lower than n squared for big O notation for upper bounds would not be correct, would not be identifying this sorting algorithm, this sorting example. But I know that at the same time, the base case scenario, it's going to take n time. For lower bound, can I say n squared? If you say n squared for lower bounds, you would just omit, like basically if I'm saying like this is the n squared, you would basically omit the base case scenario. Like, because this array could be sorted in n times, like the n operations. Then what you did is you omitted with the lower bound, higher lower bound, and then you neglected the best case scenario. So here, what we are doing is basically putting bounds for some algorithms to analyze to see they are like where they fit actually. So the worst case is also here, the best case is also here, but what I do is defining upper bounds and lower bounds to capture all the events that's happening here. So if I say n is a lower bound here, then that's fine, because like lower bound will cover the best case scenario. Lower bound is also covering the worst case scenario. And an upper bound here covers the worst case scenario and the best case scenario. So here, I would like to emphasize one more time that bounds are not related to the worst case or the best case. I can be interested in like the worst case scenario of the sorting of an array. Also, I might be interested in the best case scenario of sorting an array. And what I want to do is, for all of these scenarios, I would like to set boundaries, like upper bound and lower bound. And these bounds needs to be closer to the functions itself so I can make precise predictions. So we talked about the upper bounds and lower bounds and the worst cases and best cases. So another confusion is like, then how can we compare these bounds? So if I'm saying here I have constants, 150, 2 to the 100, it's still constant. And I have logs, I have polynomials, I have exponentials, I have factorials, and I have this guy over here. So which is the worst possible answer of like for an algorithm actually, like it's basically expanding and expanding. So if I want to do the order from smaller to the higher, it's going to be like this. These are smaller operations, these are higher operations, and if you see something as a higher operation, it means that that term will dominate the rest of the function. And for example, the exponential will always dominate the polynomial is always dominating the logarithms. Like I can just quickly, so this is like a linear function, which is y equal to x. Whatever you put here, you get the same thing over there. And the logarithm actually here, something like this. It's increasing, but with a limitation. It's not like a polynomial or like some n square like this. So these could be upper bound for a logarithm. That's why the linear functions or quadratic functions are greater than logarithmic functions. And here, the base of the logarithm does not matter, because in the end, the logarithm will still behave around this line. So here, there's a small example. I wish I could have shown you more, but like I'm going to keep it short. So here, what you would do for calculating this equation, basically, you multiply the terms, right, with this one. So here, there is some polynomial. Here, there is exponential. Here, also exponential, but who dominates? 3 to the n dominates because the root of the exponential is greater than the other root of the exponential. And here, when you look at that, so you can just simply say, okay, big O of 3 to the n is the answer, upper bound. But is it like that? Because like I am also multiplying these values with these ones here. So could be 3 to the n log n because of this product here. And this is still could be log to the power of n. And also here another with a polynomial actually, n 0 to the 1 times 3 to the n. So here actually I'm grasping the most of the growths because like this is exponential and this is basically polynomial. So here if you look at the exponential and polynomial, I had exponential and power of logs before, but here n to the power of 0.1 times 3 to the n is giving me the big O notation because it is the ultimate upper bound for this function. So the answer would be 1 times 3 to the n. So always like consider these cases, like don't get confused with, okay, this is n, but there's something, some function here. So it's not going to be a linear function or whatever, but it's still a polynomial function. And for large enough n and for some c, it can be upper bounded with this notation. Thank you so much for listening to me. I hope you understood the lecture. So I try to keep it brief and see you in the next lecture.